All right, the next type of acid base we're going to talk about is Lewis acid and base. Same Lewis as in Lewis dot structures. This is a different perspective. This is looking at molecules from the electrons, where Bronsted-Lowry is looking at it at the protons. This is looking at it at the electrons. So it's a different way of looking at it, but you get the same answer. And this is kind of more the preferred way. The reason is because, once again, so Arrhenius only explained H plus and OH. Bronsted started explaining more about different molecules that aren't obvious that has an OH, like ammonia. But then Lewis wanted kind of a way of like describing everything, including chemical reactions that don't even involve H plus ions or hydroxide ions. So basically Lewis was like, well, chemistry is based on electrons. It's not based on the protons or neutrons. That's not chemistry, that's physics. Chemistry is basically sharing and the breaking of bonds, which is all about electrons. So Lewis' way of defining it is really more of a all-inclusive and more of a the proper way of talking about chemical reactions and any type of reaction. So that's what we're going to kind of deal with now. And we're going to kind of talk about this more throughout the semester. This is how I'm going to be like talking about reactions. Okay, so a Lewis acid in this case are electron pair acceptors. They are things that accept electrons. Don't think of H plus ions and hydroxide anymore. You need to start thinking in terms of electrons. So an acid, if you think about it, has a positive charge or partial positive charge, right? Partial positive or positive charge. That's the charge on acids. So acids are going to accept electrons. Electrons are negatively charged. Remember, opposites attract in chemistry. So electrons go to the positive charge. So Lewis acids are acceptors, where bases are negative charge or partial negative. So what do they do? If they have a negative charge, they have extra electrons. They want to get rid of the electrons, therefore they are a donor of electrons, electron pair donors. All right, so Lewis acid are acceptors, Lewis base are donors. Okay, so Bronsted acids are not Lewis acids because they cannot accept an electron pair directly. Only a proton would be a Lewis acid. And so the Lewis definition leads to a general description of many reaction patterns, but there's no scale of strength as in the Bronsted-Lowry. So there are pros and cons of each of them. The Bronsted-Lowry kind of gives you pK values. The Lewis doesn't. It's just basically if you have something that has filled orbitals with electrons and you have something that has a vacant orbital, all right, or that has a positive charge, these electrons are going to go to it, okay, and you're going to form a bond. Okay, trust me, we will talk a lot about this in class if you haven't had the lecture yet. Okay. Okay, so here's kind of an illustration, just kind of showing you this curved arrow way of doing things. We're going to be talking a lot about these curved arrows. I've kind of been doing them. This is what's called a mechanism. It kind of shows the flow of electrons. Okay, so these arrows are showing the flow of electrons, where are the electrons going. All right, so the electrons from the oxygen, so this is acting as a Lewis base. Why is it the base? Because it's donating the electrons. Okay. Boron, I haven't talked about this. I'm not sure if I've talked about it yet in class, but boron is special. Same for aluminum. Boron and aluminum do not follow the octet rule. Okay, that's a funny looking B, but that's a B. They do not follow the octet rule. They are happy and neutral with only 6 electrons, 6 valence electrons. Okay, so what happens is boron has, let's say it's attached to the fluorines, like in this case the boron trifluoride. And then it has this empty p orbital. Now this is the same for aluminum. Aluminum, AlCl3, same thing. You have 6 electrons, 2 here, 2 here, and 2 here for a total of 6, and you have this empty orbital. Now boron can go to octet, so can aluminum. It can accept 2 more electrons, but it's neutral and it's happy with only 6. So because of it, it acts as a Lewis acid because it can accept more electrons. So boron is accepting electrons, all right, acceptor. This is the donor. Okay, so this is the Lewis acid. This is the Lewis base. So it's donating the electrons to the Lewis acid, and you get this new molecule. All right, you formed a covalent bond. All right, oxygen is positive because it lost the electron. Boron is negative because it gained the electron. Okay, and that's basically Lewis acids and bases. We will talk a lot more about it in class. This is just kind of a chart just to kind of show you some Lewis bases. Lewis bases can accept protons as well as Lewis acids. So it's going to get a little confusing because a Lewis base can also be a Lewis acid. Okay, just like what we saw in the Bronsted acid and base example. All right, most oxygen and nitrogen containing compounds act as a base, okay, because they have lone pairs. Pretty much anything that has a lone pair on it can be a base, okay? Anything that has a hydrogen attached to the thing that has a lone pair can act as an acid, okay? So for example, here's a perfect example. Some compounds can act both as acid bases. It depends on the reaction. So alcohol, for example, actually is both a base and an acid. Why is it a base? It has lone pairs. So it can share these electrons with another compound. But it can also act as an acid. Why is it an acid? Well, the hydrogen is very partial positive because it's attached to an electronegative atom. So it can also act as an acid. We will talk about in class how you recognize if it's acting as an acid or a base. Okay. This compound, the ether, all right, is just a base. It can act as an acid because you don't have any partial positive hydrogens. Remember, hydrogen attached to carbon is neutral. All right, this is really acting as a base, and these act as a base. We did see these ketones can act as an acid, but mostly they act as bases. All right, carboxylic acid obviously is an acid. I mean, it has the word acid even in it. So why is it under the base category? Well, these lone pairs can act as a base. These electrons can be donated to something that is very partial positive or has a positive charge to it. Okay, so the first time you're watching this might be very confusing. How do you know? It will all come together, I promise. Okay, this slide is kind of a summary of the chapter. All right, kind of tells you organic chemistry is the chemistry of carbon compounds, what an atom is, electron structure and orbitals, what a covalent bond is, sharing electrons. Valence bond theory is where a bond is basically an overlap of these orbitals. Difference between sigma and pi bonds, hybridization. All right, by now hopefully you're experts at hybridization. And then they talk about electronegativity, bond polarity, what Bronsted-Lowry acid bases are, what Bronsted-Lowry acid bases are, and what the difference between a Lewis acid and a Lewis base. Okay, and that's kind of the summary of the chapter. All right, let's kind of do a real quick problem. There's a quick problem here we can do. All right, so rank the following substances of order of increasing acidity. Okay, so I mean, you can do it that way, but let's just kind of talk about it by looking at these molecules and their pKa's. Which one of these is the most acidic? Which one is the stronger acid? Well, your definition is whichever pKa is the lower number, that's the stronger acid. All right, so you have 19.3, 9, 9.9, or 4.76. Obviously, this is the lowest, so this is the strongest acid. Okay, what would be the weakest acid? All right, well, whichever one has the highest pKa, which would be acetone. So this is the weakest acid, WA for weak acid. Okay, here's a question. What would be the, in terms of base, which one is the strongest base? Which of these four would, in the basic form, would be the strongest? So that would be the one with the highest pKa. Right? The higher the pKa, the weaker the acid. However, the stronger the base. Okay. So if you had to do this, so if you did have to do this problem, rank in order of increasing. So acetone would be first. This would be number 1. Number 2 would be phenol. Number 3 would be this 2,4-pentane-dione, and number 4 would be your acetic acid. All right, which is exactly how they show it there. All right, draw an electron dot structure of acetonitrile, which contains a carbon-nitrogen triple bond. So a carbon-nitrogen triple bond. How many electrons does the nitrogen atom have in its outer shell? Well, that you should be able to tell me automatically. What does everything have? All right, I'll give you a hint. Octet rule. All right, if you said 8, good job. All right, how many are bonding and how many are non-bonding? Well, if you have a triple bond nitrogen and there's 2, 4, 6, that means nitrogen needs 2 more, so you have 1 lone pair. So that means this carbon must be attached to the other carbon, and then the 3 hydrogens are around that carbon. So that would be the structure for acetonitrile. All right. and there it kind of shows you in the dot form. Okay, so that is it for chapter 1. Like I said, most of this we will do in class, but this is just kind of if you want to watch it afterwards, or if you want to watch it before the lectures, you have it.